Okay, so here we have another problem that you're going to need to submit dealing with scatter plots and correlation. This happens to talk about a student wondering if tall women tend to date taller persons than do short women. Right? So they measure, let's see, 1, 2, 3, there's 6 women that they measure. They measure the heights of their dates as well and ask to make a scatter plot of the data. Okay, and what do we expect the correlation to be? So let's see what that might look like. So our scatter plot might look a little something like that, like this right over here. Alright, so we've got 1, 2, 3, 4, 5 data points, 6 data points. Alright, not very many data points, but still, alright, if we look at this, would we expect that correlation to be positive or negative, near plus or minus 1 or not? Explain your answers. What would we have? Well, we would expect it to be a positive correlation because when my x values go up, my y values seem to be going up as well. If I look at this, kind of seems to be positive. Right? We seem to have a moderate relationship here. Right? And so that would mean that we're not near plus or minus 1 on our correlation. And that's because this woman that is 70 inches tall seems to be a high leverage point possibly. Right? That over here, this point over here is pretty far away in the x direction from all the rest of our data. Right? The y value is close to everything, but it's pretty far away in the x direction. What does that mean for us? What that means for us is right now, we might have a least squares regression line that sets up in there, but if we were to take that point out, our least squares regression line might be a lot tighter and closer to all of our data, right? So if we can think about this kind of as being a lever that's pulling down this least squares regression line, and here is a fulcrum for that lever to be able to lift all this data, then we would say that, yeah, that's probably a high leverage point. Okay, so very important to understand. Now, the next step is to find the correlation step by step using the formula on page 154 of your textbook. Right? So the formula that we're going to use that is in your formula book is that R is equal to 1 over n minus 1, the summation of x sub I minus x bar over s sub x times y sub I minus y bar all over s sub I, right? Which would be 1 over n minus 1, where n in this case is 6, right? We have 6 samples, that's so 1 over 5, right? And then our x sub i's, well, we know our x sub i's, we know our y sub i's, and I've just written out the first few here, right? So my x sub I, the first one is 66, right? The next one is 64, the next one is 60, whoops, excuse me, put that in the wrong spot, right? The next one is 64, right? The next one is 66 for the x sub i's. The y sub i's, right? 72, 68, 70, right? Then we also have to calculate these other pieces, right? We need to calculate the x bar and the s sub x, and we can do that using our calculator. So I can come over here, oops, clear this out, stat edit, and I have the information already entered into my calculator, right? So if I want to calculate the x bar, y bar, s sub x, s sub y, come over here to stat calculate, one variable statistics. My x list is in L1, so there's the information for my x bars. And if I do the information for my y list with L2 is where my y list is, there I have the information for my y bar. So with that information, I'm going to fill out the rest of these details. Right, and I would be able to set that up for all of these values. Now, I can get that information, right, calculated more easily in my calculator if I need to kind of show the setup and I want to double check, right, with what my roundings are. What I can do is come over here, come back to my stat list, and on L3, right, on L3, I'm going to do the following. I'm going to have L3 be given by parentheses L1 minus 66 divided by 2.10. Right? That's going to be L3. So what's that giving me? That's giving me all of these, x sub I minus x bar all over s sub x. In L4, I'm going to put in parentheses second L2 minus 69 divided by 2.53. Right? Set that into L4, and so these are all the y sub I minus y bars. Okay? Now, I need to find their product, right? I need to find their product, so L5 is going to be given by second L3, L3 times L4, so that's going to be L5, right? And then in L6, what I'm going to come in here and do is I need to find their cumulative summation, so I'm going to hit the following. I'm going to hit second stat to get into the list. Operations, I need the cumulative sum, right? And I want the cumulative sum of L5. And so, boom, there I have to my cumulative sum, this 2.8233. Okay? Now, what I care about is the next number, 2.8233 divided by 5, because it's 1/5. And if I do that, I have about 0.5647. So my R value in this case, doing those calculations, would be, that means that R is approximately 0.5647, which would indicate I have a moderate relationship. Okay? Now I can of course check that and double check it. If I come over here, right, and I've already put my information in, right, I've set up my regression line already, and so I can see that this does kind of match what my initial was. Okay, and we said, hey, a moderate relationship. Well, I can go stat, calculate 8 for that linear regression. My X list is in L1, the Y list is in L2. Right? I can store the regression equation into Y1, and if I come over here, right, I get 0.5653, right? Very close to my answer. The reason for the difference, of course, is in the rounding that we had for the standard deviation of X and the standard deviation of Y. So there's my R value. Okay. Now, how would I determine the coefficient of determination from the correlation coefficient and figure out the value? Well, what do we know? The correlation coefficient is R, right? So the correlation coefficient is R, while the coefficient of determination is R squared. So R squared would simply be that 5647 squared, right? And I know what the answer should be close to. It should be close to this 0.3196 that I got. And if I double check it, 0.5647, right, take that number and square it, that's very close to the value that we said. So this is 0.319 or 3189 approximately. So 0.3189. And once again, generally we're going to say that that's a moderate relationship. Okay, so how do I determine? I square the correlation coefficient, right? So if I square the correlation coefficient, to get the coefficient of determination. Okay, going to square that correlation coefficient to get the coefficient of determination. All right, and then use a calculator to find that least squares regression line and verify the value that we found in B and C. Well, we've already done that, but we're going to do it once again so that we recall how to do it. All our information for X and Y is in L1 and L2, right? That's where we had the X and the Y information. We said stat calculate. We're going to want A plus BX for our regression line, so that's 8. right? We're going to calculate that equation, and we see that it's going to be 24 plus 0.68x. And we already talked about looking at those values, how they were close. So, notation, y hat, the least square regression line, is 24 plus 0.68x. Okay? Now, using your answers in B, C, and or D, do the data show that taller women tend to date taller individuals? All right, well, if I look at my data, it does seem, right, it does seem, okay, why? And that is because there seems to be a positive, moderate, linear correlation between the height of the individual and the height of the person that they are dating. Okay? Of course, we could come over here and check the residual plot to see how good our linear fit might be, and that would be done as follows. I would come in, and I've cleared out my columns, right, and I could come into L3. I could come over here into L3 and say, let me second stat, let me plot the residuals that I have, right, in L3, right? So here are my residuals that I got from my previous, from my regression analysis, and it is important that you plot the residuals of the last regression analysis that we did. Okay, and then I can come to second plot, and I can turn my scatter plot on, and let me actually go to plot 1, right, and I'm going to change it from L1 and L2 to be L1 and L3 to do my residual plot. Okay, I'm going to go to y equals, turn off that, and go zoom 9, and there's my residual plot. And if I look at my residual plot, there doesn't seem to be any great pattern to it, right? There are my values in comparison to the 0, right? They seem to be nicely distributed, so a linear plot would be appropriate, okay? And then use the model to predict the height of a person that a 6-foot-tall woman would date. Is this a reasonable approximation? Why or why not? Show your setup. Well, this is what it would look like. First, our equation, right, we're going to evaluate it at a 6-foot-tall woman, the input x, which would be 72 inches. So y hat at 72 is equal to 24 plus 0.68 times 72. And that value is 72.96 inches, right? Now, that's all I did, 24 plus 0.68 times 72. Now, of course, I have actually, right, stored that equation into y1, and so I could come over here and just say second trace y1 at 72 and get a little bit more precise value, which is about 73 inches. Okay? Now, is this a reasonable approximation? Why or why not? In order to answer that, we need to look at our plot. Okay? We have someone that's 70 inches, right? And if we were going to have someone that was 72 inches, right, they would be up here, right? That this would be if I had someone that was 72. Okay, now, is that going to be close to our line, right? Well, yes, it does seem, right? Reasonable approximation, we would say the following. We could say, yes, it's reasonable because 72, right, is going to be, and really we're saying that that's the point 72, 73, that is close to the other data point, 70, 71, right? So it does seem to be reasonable. Now, you might say, but this point seemed to have been a high leverage point. And while, yes, that's true, we also have to acknowledge, right, that there's fewer tall people over here, and, you know, a lot fewer tall people over here as well, right? So we could get into the idea of regression to the mean in this case, but really this is talking about why or the why not, right? So if you want to say that it's not very reasonable because this would be another possible high leverage point, possible an outlier, you could discuss that. But in the big scheme of things, 6 foot, while it is a bit taller than someone that is, only 6'10", or, at 70 inches, or only 6'6", right? It may not necessarily be that far away. Okay, so you just want to be careful with your answers there. All right, this was a little bit long-winded. Appreciate your time and attention. If you have questions for clarification, please make sure that you ask.